Now, just a little bit of review of what we have established till the previous lecture. So, for example, in the last lecture we showed, in fact last to last lecture we had shown G star HKL is perpendicular to the plane HKL, which means a reciprocal lattice vector with components HKL in reciprocal space, which means this is just a short form, this is a short form for a vector which should be written fully as HA star plus KB star plus LC star. That is what is meant by a reciprocal lattice vector G star HKL. The components are HKL, but components are always with respect to some basis, and when we are saying a reciprocal vector. So, the components are with respect to the reciprocal basis, and the reciprocal basis is A star, B star, C star. So, a reciprocal lattice vector HKL is perpendicular or is normal to the real lattice plane HKL. So, real lattice plane HKL, you know the Miller indices HKL. So, its intercepts are A by H, B by K and C by L on the x, y and z axis of the real space on the A, B and C axes. So, this was one of the relationship we established. The other relationship which we established in the last class is that the length of this vector, length of this same vector is exactly the reciprocal of interplanar spacing DHKL. So, the length of G star HKL is reciprocal of the interplanar spacing DHKL. These, as I told you, these two are the most important relationship. In fact, this is the reason for existence of reciprocal space. If these two properties were not there, reciprocal space would not have been defined at all and would have been no use for us. So, these two are the two critical properties. Then we defined a quantity called metric tensor, because we found that if we only know the components, then component wise product and their sum is not the dot product unless and until the basis is orthonormal. Unless and until basis is orthonormal, then component wise product and their sum is not the dot product. So, dot product requires a little bit more involved formula, which is shown here for you. So, that x dot y becomes x transpose G y, where G is the reciprocal G is the metric tensor defined by the dot products A I and A j, where A i's are the basis vectors of the space. So, for every basis you will have a corresponding metric tensor, and then you can find the dot product in that basis. We also introduced a useful coordinate we introduced coordinate transformation in general, and the general coordinate transformation we called Q. So, that symbol we will stick to in this course. You can call it, it is only a matrix. So, you can call it anything P, Q, R or whatever, but we have decided to call a general coordinate transformation matrix as Q. So, Q is a general coordinate transformation matrix, whereas for the special case of a transformation matrix from crystal basis to orthonormal basis, for that we have used the symbol C. So, C we will use for basis transformation matrix from crystal basis to orthonormal basis or Cartesian basis. And what is the definition or what is the property of C? The property of C is that if it multiplies a column vector, the components of any vector written as column. So, what is written as x 1, x 2, x 3 is the components of a given vector written as column, and you multiply it with the coordinate transformation matrix, then it will give you the components of the same vector in the orthonormal system, the corresponding orthonormal basis. So, from a general basis, the vector is being transformed or its component is being transformed to orthonormal basis. Then we ended the last lecture with an interesting result that this metric tensor and this coordinate transformation matrix from crystal to orthonormal basis are related by this interesting relation that if you know C, you can calculate G. C transpose C is G. Of course, G is much easier to calculate than C. So, this equation really is not a recommendation for calculating G, because once you know the lattice parameter, you can directly calculate G in terms of the lattice parameter, because it is simple dot product A dot B and things like that. So, A dot B is A B cos gamma. Similarly, all 9 terms are written very simply for G. So, you will not use this equation really to find determine G from C. If it so accidentally happens that you know C and you are not knowing the lattice parameter, then you may use this in that case, but otherwise it is not a calculational recommendation, but it is an important relation which simplifies many algebraic calculations and can be used for establishing many properties, which we will see soon. Then similarly, the corresponding coordinate transformation matrix in the reciprocal space we are calling C star. So, we are having 3 coordinate system now. We have the crystal coordinate system, A, B and C. Then correspondingly we find the reciprocal coordinate system A star, B star and C star, and we have then the orthonormal basis E1, E2 and E3. So, what we are doing is that we are setting up a matrix which takes us from crystal basis to orthonormal basis, that is being called C, and the corresponding reciprocal basis if it is being taken to the same orthonormal basis. Saying orthonormal basis also does not uniquely define it, it can have many different orientation in space, you have to choose one. So, there is a lot of freedom in choosing your orthonormal basis. For example, we did when we introduced this C matrix, we tried to calculate by taking E1, I have not drawn it that way, you can see here, but we took it E1 as parallel to A or A parallel to E1. That was one of our choices, but whatever choice you make, that is not necessary. Some people make parallel E3 to C, or as I have drawn, none of the axes may be parallel. All that is required is that there is a fixed orthonormal coordinate system which has a fixed orientation relationship to the ABC system, then C is defined and any such C will work. And once C is defined, a corresponding C star is automatically defined. Once C is defined, because once ABC is defined, A star, B star, C star is calculated in terms of ABC. So, C star and C are not independent, they are related, and one of the exercise of the last lecture was also to establish that relation, where we showed that C star was nothing but C inverse. So, the name reciprocal is very much justified, everything turns out to be reciprocal in this space. So, the corresponding coordinate transformation matrix C star you find is nothing but inverse of the C matrix. Only care which has to be taken that when we use this when we use C matrix, as we have shown here C matrix, we write the vectors as column matrix, whereas when we go to the star space, when we go to the reciprocal space and we start using C star matrices, we start writing our vectors as HKL, row, we start writing them as row, and if you write them as row, then your matrix multiplication by the rule of matrix multiplication, matrix multiplies it from the right instead of multiplying it from the left. Some people do not like this change from row to column. They say that once and for all we have decided that all vectors, whether in real or in reciprocal, we will always write it in column. If you decide that, you can do that, then you can take the transpose and then you will find that H naught, K naught, L naught. If you take the transpose of the above equation, transposition changes the sequence of the matrix, as you know, and you will get HKL. Then you will say that the corresponding transformation, these things keep means make lot of confusion, and even I keep getting confused when I go from one book to the other. One has to be careful what is that book's convention, whether it is C inverse or C inverse transpose, because C inverse need not be a symmetric matrix. So, its transpose will be a different matrix. So, whenever you come up with a new paper or a new textbook or a new document on crystallography or this kind of transformation, you should make sure what is the convention. So, if the convention is to write the reciprocal vector also as columns, then one transposition comes. So, it is a question of choice. Some people say that this is more neater, that everything is column, but then they have to live with an additional transposition over inverse. Some people say why transpose, just to start writing the reciprocal vectors as row, then it is simply inverse, and inverse in a way is easier to remember because you are working in a reciprocal space. So, everything is inverse of the real space. Now, we also have established one relation in the very beginning, that determinant of this coordinate transformation matrix, the matrix which transforms the crystal basis to orthonormal basis, has this important property. Determinant is volume of the crystal basis, volume of the unit cell defined by the crystal basis. So, A, B, C will always define a parallelepiped, they will have a volume, and that volume will be determinant of the C matrix. These are all established, we have done this.